Hello, everyone, and welcome. Thank you for joining us today to hear about transaction management in the context of ConfD and NSO. My name is Nabil Mishraf. I'm Solutions Architect at TALEF, and I have my colleague Connie Oholt with me today, who will be presenting this very exciting topic of transactions. If you have any questions during the meeting, please use the Q&A tab, which you will find on the right side of this window. We will be able to answer your questions as they come in, or we can bring them up to Connie's attention at the right time, probably at the end of the presentation, or if there is a content that's relevant to your question that Connie will be presenting, we can then bring those questions at that time. So with that, I don't want to delay this any longer. I think we have some great content to go over, Connie. So I'll let you take the mic from now.
All right, thanks, Nabil. All right, so the ConfD transaction manager is actually a core part of ConfD. For those of you who worked with ConfD, some of you I saw in the participants list with ConfD for years. You know all this stuff, right? But it takes a bit of work to actually get grips on it and actually what you can do with it, and then see the opportunities and not just that it's in the way of what it's doing, that actually the benefits that it's providing. So we try to show that here, but also from a managed perspective, managing ConfD-enabled and non-ConfD-enabled devices using netconf, for example, or when it comes to CLI, we touched on that a little bit. Just to see it from, for example, the NSO perspective, the Network Service Orchestrator, which is a Cisco product that can do all these things, wonderful things, and interact with the ConfD transaction manager. So the past few presentations I've done, I've been pretty clear that I've been a little bit inspired with the language from this very, very good book that Martin Kleppmann wrote here and released, I think, a year ago, and might be two actually now. So it's really good at describing, like from the academia kind of point of view, the not only data-intensive applications, but also it dives deep into all these concepts around transactions and why transactions are there, and also what the problems are with transactions and how do you scale with transactions, for example. So I can recommend this book. It's a really good read, and some of the language I borrowed from that to be more generic than the kind of in-house language that we had at TALEF for a long time. All right, so what is transactions? Well, as it says here, transactions are a way for a database to provide strong guarantees so that the application can be simpler. So when we talk about the application here, we're not talking about the application that actually interacts with ConfD. Okay, that can be simpler, of course, too. But we're more so talking about the manager of something like a bank account or a device in a distributed network. And so transactions is a way for an application that to group then several reads and writes together in one single logical unit. And conceptually, all the reads and writes in a transaction are then executed as one single operation. So it's either the entire transaction succeeds, then you commit it, or it fails, you abort, roll back. If it fails, the application can then safely retry the same transaction or change the transaction so that it doesn't trigger some validation error or something like that. So with transactions, then error handling, and this is the key part, error handling becomes much simpler for the application because your application doesn't need to worry about partial failure. For example, the case when some operations succeed and some fail, how do you roll those back and what do you do next and so forth. To handle all that from a manager, that's what I mean when I say an application, is very tricky unless you actually done it with applications. So if you look at it, most people try to stick with transactions and only divert for them if necessary. By people, I mean applications that do implement a distributed network. So without transactions, then various error scenarios like processes crashing, network interruptions, power outages, the disk becomes full, unexpected concurrency, you have several writing to the same place at the same time. This means that the data can become inconsistent in various ways. And so the transactions are the abstraction layer here that allows an application to assume that the database cannot become inconsistent. A large class of errors can then be reduced down to a simple transaction abort. And the application or the manager just needs to try again. To set the application again, try not to violate some validation requirements and so forth. But not every application needs transactions, and sometimes there are advantages to weakening the transaction guarantees to, in the worst case, abandon them. For me, the worst case, abandon them entirely. For example, you want to achieve higher performance or higher availability. We'll talk a little bit about that later. Some safety properties, of course, can be achieved without transactions. So a nice use case for transaction management is network management, which is what we talk about here, but it can also be a bank account. So how do you figure out if you need transactions? Well, in order to answer that question, we first need to understand exactly what safety guarantees transactions provide and what costs are associated with them. So we'll try to dive into that and take a look at that in this presentation. In this bank account kind of example, I bring up ACID. And what does ACID mean there, real quick? Most of you probably know. If some of you don't, here it comes real quick. You can look it up in for example, the book that I mentioned earlier. So atomicity or atomic is the A, and some people call it both atomicity or atomic. So what it means is that there's either an all or nothing operation. You can't have partial success and you can't have partial failure. Everything either must succeed or must fail. That is a guarantee if your database conforms to the atomicity principle there. So the second letter C, that stands for consistency. And what consistency means is kind of related to atomicity, but it's basically that the operations that are performed on your database must be done in a predictable way and can only change data and in allowed ways then. So for instance, you can't decrement the balance here. Let's see if this works. You can't decrement the balance here to 0. That would be an inconsistent operation. Past 0, I mean, that would be an inconsistent operation. So that's about you violating some validation here. So you violated the constraints or the rules of this table. So and that's not allowed. And the I in ACID, that stands for isolation. So isolation, it just basically means that one transaction cannot impact the outcome of another transaction. So now there's a bunch of ways that this is implemented. One common way is through the use of locks, and this is what ConfD use. But the concept of isolation also means that if there's two kinds of attempts to modify the data, on one of these rows over here, so modify the data in one of these rows over here so that if we have two different transactions that are simultaneously trying to do something similar on these two rows, only one of them then must succeed. So you can't have concurrent updates on the same row. That is not allowed under ACID compliance system. And in this example, if you have two things that are the same at the same time trying to modify these rows, one must succeed and one must fail. So if you have like two transactions coming in here that try to do the same thing or different things, only one of them must succeed, so that you don't have a mix of them, like you deduct from the bank account at the same time adding, and then you have a deduction, but the other addition doesn't go through or something silly. Of course, you don't want to see that with your bank account. You want to do 1,000 there in this first bank account that you had. So the last layer in ACID then stands for durability. So durability basically means that if there's kind of a power outage or a loss of state or anything that kind of gets in the way of the database acting as it should, there's no data lost. And that's what D is basically. You persist the storage, put it in persistent storage. And what ConfD does is, and NSO as well, just persisted to disk in a journaled copy of the database that's in RAM. So typically then when you hear the term transaction, typically, I mean, most of the time, when you hear the term transaction, that's probably must satisfy all the letters in ACID then. All right. So you've probably seen ConfD, you've probably seen this picture, you got some YAG models that you write, and then you put in the ConfD, and that becomes the database schema, and then that renders the northbound interfaces. And then you have your applications that integrate with ConfD. You have the manager here, what might be NSO, that maybe through, sorry, didn't intend to click there. That changes the configuration, and the applications get the configuration changes, or an external database is updated, or someone reads some operational data or something like that. Then there's this core engine that enables all of this with changing the configuration in particular. And that one we bring up here in the middle here. It's really the key part of ConfD and also NSO. It makes sure that everything is done in an ACID manner, mentioned on the previous slide. And the transaction manager, it looks something like this when you show the running, well, a commit to running only, a transaction that where you haven't enabled the candidate data store or anything like that in ConfD. And so you might, for example, have a CLI commit, a netconf config, then there's a check to see that you write the minimal diff only. If you're writing something that already exists in the database, that will be parsed out so that we only have a minimal diff that goes into the database. And then there's this transaction lock that's taken that we talked about. This is not the global lock or anything like that. You can lock the writes to the running data store over netconf or CLI or management API. CLI exclusive would be the way to do it in the CLI. And this is different. This is as soon as you do, as ConfD tries to write something to the database, there's a lock to guarantee that there's not intertwined attempts to write to the data store at the same time. You get unpredictable results. So that's taken there, and then you have some hooks that can be custom hooks to write something into operational data store or write some configuration that's not visible over, for example, the kind of netconf or restconf APIs or something like that. You can do transforms to lower level kind of YAG models from the YAG models that you want to show northbound over the northbound interfaces, or some of them. And then you come to a validation phase where, you know, must expressions, patterns, ranges, and so forth are checked. And there's also code that can be executed through validation points if you have a need for that. And then you come to the prepare phase. So this is where CDB writes all the changes down to disk, to, you know, the durability in the ACID. If there's HA, then the changes are sent to the standby node if this is a master, for example. And then you have done what you need in the prepare phase, go to notify subscribers, and there might be subscribers already in prepare phase. And this is basically to check, for example, oh, well, is my hardware ready for receiving this configuration change here, or should I abort it at this stage? And this is your last chance here to abort it. So therefore, many users of ConfD actually use this to do some extra checks that you don't want to do in validation phase. In validation phase, you want to check the actual configuration, if that's valid or not. You don't want to check against some state or something like that. But there might be state things that needs to be checked, and this is a good place to do it. In that case, if you actually need that. And here we can abort, and then nothing will be set into CDB. It will be actually the transaction complete mark will not be written, so it will be just reverted, even in the persistent storage, of course, and the transaction will be unlocked. If it succeeds here beyond the point of no return, and you discover some error here, you probably send an alarm or something like that to the manager that initiated this transaction right here. So this is where CDB or your custom database or a mix of them, CDB for some data, that's the ConfD data store, and your external data store for something else. That's very common as well. And then the subscriber is notified, but this time they're notified to say that, okay, this commit actually completed. This is the configuration data that you said through this prepare phase and validate phase that you could actually implement. So go do so and let me know when you're done. And when the subscriber application has said, okay, we're done, we made the changes, then the transaction is unlocked. And why ConfD is waiting for the subscribers to notify that they are done is because, of course, you don't want another transaction to come in at the same time as they are trying to finalize writing the data for and reading out the data from CDB, the configuration changes, and then you don't want another configuration go in there and change that configuration while you're reading it as an application. And this may be, one application that does this, or it might be 1,000 subscribers in the extreme case, which we also have seen. All right, and they are prioritized, so you do it in priority order and so forth. And you subscribe to different parts of the configuration and all this. We won't go into all the details of that. All right, unlocked. So from the NSO side, how does this look? Well, NSO, the high-level overview, this is an example of a manager then. This is a service orchestrator. In the NSO overview, you don't really see transactions. It hides in here somewhere, a service manager, device manager, CDB. We'll probably put it in there somewhere together with the network element driver. Another difference between ConfD and NSO is that, well, NSO has no applications at the southbound part here. Same interfaces going northbound, netconf, resconf, CLI, etc. But you have a network element driver that manages multiple devices at the same time. Could be netconf devices, but it could also be like CLI, REST, and so forth type of devices. And then you have service YAG models that maps to device YAG models. The service is sort of a higher level view of what's going to be done then down in the devices. So this might be multiple device types from multiple vendors, but a service needs to access these devices, set the configuration of these devices to provide a service to its service developers, for example, service provider, service providers, customers, or other parts of the system. All right, so an NSO transaction, very similar to ConfD's transaction manager. Well, it shares a lot of code with ConfD. So the NSO transaction manager, if you look at this as an example of a manager's transaction, it looks very simple, especially when you only use the running kind of data store with ConfD. They are extremely similar. So here too, you do a CLI commit, you do some changes. Now, the difference here is that NSO will do more for each of these steps, especially transaction hooks here. There's not just, as with ConfD, custom hooks and transforms, but you compute undo information for each of these service service instances, and does the create for those. And this is done after the transaction lock is taken. We'll talk about it later, but it can also be before the transaction lock is taken, parts of these things that you do here. So these services will map then with templates or code into device configuration. And so What's also part of this is validation, very similar to what you saw with ConfD. With prepare phase, there's more being done. There's kicker evaluation. That might be things that have thresholds and can be triggered, and certain events that happen that make you do this or that. But the same thing here, there's a CDB database in NSO2, and when it comes to writing it to disk, that's the same. Using HA, of course, there's more things you can do with HA here, but it's basically the same thing when you look at it from a transaction manager perspective, at least. Well, there can be a custom database. What actually happens here is that the device manager, there's a service manager and device manager that you saw here in the previous picture. The device manager will prepare then the NEDs or commit queues if you have lessened the consistency a little bit. We'll get to that later, what it means with commit queues. Looking at from a manager perspective, if you want to not do the kind of strictest of network-wide transactions. Well, okay, so if it's a netconf device, in this prepare phase, NSO will send the netconf commands to the device and validate it. So if you have the candidate data store available, NSO will not commit at this time. Or if you have special transactions, which we'll talk about later, NSO does not have to commit actually at this phase already. NSO can say, okay, I have 100 devices. I want to send the configuration to their candidate data store and validate. If it's a CLI only device, NSO will have to send and activate the new configuration that is validated and committed in the same instance here. So if you here have a device that fails in this phase, if something fails here with netconf, well, you're only in the validation phase. So you can just abort the transaction and say, okay, sorry, clicked again. Abort the transaction and say, okay, no changes to any device, and all those 100 devices will not have the configuration set. But with CLI devices, you do have to set it here and prepare running. So that makes it a bit more difficult. You have to send the undo configuration to such a device if another device fails, for example, at this stage. So then we go into abort or commit. Let's say we're going to commit then, and well, this is where NSO would send the commit to the ConfD, for example, enable device of a netconf. If you have netconf enabled, or if it's RESTconf or something like that. All right, so if we look at it from a sequence diagram kind of thing here, this is just to show that you have a RESTconf client, and then you have a couple of RESTconf servers. You have a netconf client and a couple of netconf servers. And what's the difference between RESTconf and netconf here? Not much if you only have the running data store enabled. You will typically lock running, do an edit config unlock running with netconf. And it's basically the same thing with RESTconf. You do a yang patch, for example, that's the same kind of thing as doing an edit config. You send all the configuration in a transaction and you commit it. All right. So what does a confirmed commit transaction actually mean then, where you have the candidate enabled? So this is taking the view of ConfD again. We're going back to the ConfD transaction manager. And you can see how there's quite a few steps added here with we go from read write, not directly to transaction lock running, but we have a commit confirmed phase. So for example, the manager is over netconf doing an edit config to the candidate data store. And then the manager says, okay, I want to commit this to running. So then you go through these phases of you lock the candidate and you validate candidate. You can actually validate candidate without doing the commit first. You can, this is what, you know, I showed in the previous picture a little bit, that you can do an edit config and then you validate, and then when you have validated those 100 devices or virtual instances, then you go ahead and do the commit, which means that if one of the devices or instances fail at validate, you haven't committed anything, and you just say, okay, undo. Just throw away that candidate. I didn't want to commit that. You just saying that to all the devices, cancel it. Okay, so you do a confirm commit, and then there's actually a timeout associated with the confirmed commit. You could have said set the timeout here in this RPC call here. It's by default 600 seconds, I think, 10 minutes. But you can set it to 1 second if you like. If you think your device is really fast, of course it is. All right, you go through the validation phase again, prepare phase like we described earlier. There's actually a point of no return here that was the same point of no return as previously. Then you actually have everything notified to subscribers and so forth. But then you have a second kind of step here where this confirmed commit needs to be confirmed by the manager within these 600 seconds or whatever you set the timeout to. If it's not, then or if someone cancels the commit, sends a cancel commit, for example, or a timeout occurs before this commit, this final commit to confirm the commit of the confirmed commit, then it will be canceled commit. And actually, ConfD will in that case notify all the subscriber applications again, but this time with an inverse configuration. And to the subscribers, it would only look like, okay, there's another transaction. I got some transaction here. Now there's another transaction and happens to be the inverse configuration. So it just undoes everything. And so this is the last resort, basically. If you have some device failing, for example, due to a validate down here or prepare phase here, one of these 100 devices, then you can, as a manager, always say, okay, this device over there failed, so I want to cancel these 99 devices or instances. Send the cancel commit to them or something. Or you lose a connection to one of these devices. And the kind of ConfD enabled or the device that has is waiting for the commit here. The timer will time out and the configuration will be reverted and so forth. And if the configuration was something that actually caused this device to be irresponsible, this could be a way to bring it back. It's just, okay, the timeout expired, so it rolls back the configuration that was bad, and we're up again and we can reconfigure it. That's the happy case. All right, so in a sequence diagram, well, you have a bunch of servers, or 2 or 1, and you have a netconf client, and so there, for example, or ConfD. You would then typically lock the candidate first, then you do an edit config candidate and validate the candidate. If everything goes perfect there, you go ahead and you do a confirmed commit. And then you confirm that commit, and when you're done, you can unlock the candidate. And this is assuming then that you don't have writable running. You have the confirmed commit capabilities enabled, and you only allow running to be writable through the candidate data store, which is typical there if you want the strictest of strict consistency in your transactions. All right, it's worth to note with ConfD, you have a transaction capability, and it's a little bit different. Why do we have a proprietary transaction capability? Well, I mean, it's not really used that much because you achieve the same thing here with a candidate, but what you do is basically expose these validate phase and prepare phase to the manager. And if the manager knows about these proprietary transaction things, you can achieve the same 2-phase commit as you saw with the candidate data store, or with the confirmed commit, it would be even a 3-phase commit. So there's still advantage, but let's say you don't do the confirmed commit, you only have enabled candidate, you have a 2-phase commit, this would be the equivalent then of a two-phase commit. You would have these proprietary tailf netconf calls that you could use, and actually NSO will use these if they are turned on, and you have a ConfD enabled device, and NSO understands these proprietary things or steps. Then it will be slightly more performant to do it that way. So NSO would in that case start the transaction, do the edit config after that, and then you have the transaction phase going in here, and ConfD would stop here, waiting for a prepare transaction before going into the prepare phase. And after notifying all the subscribers, everything went well in the prepare phase, ConfD will wait for a commit transaction or an abort transaction from the manager. Unless, of course, you as an application abort the transaction, then as with the other variants, the transaction will be aborted by the application. All right, so if everything goes well, you go in. We unlock, and we are very happy. So the sequence diagram kind of looks the same, but you have this added start transaction, prepare transaction, commit transaction kind of netconf calls, if you look at it from a netconf client or NSO or something perspective to netconf server, ConfD enabled in this case. All right, so then it's a little bit confusing when you look at this from northbound interfaces. I used netconf and restconf a little bit. So why was it that restconf didn't do a confirm commit? Well, it's because in the restconf standard, you don't have candidate support. So with full support, I mean candidate, confirm commit, and so forth. And you can also use tailf transactions with netconf. Same thing with CLI, actually, for ConfD. You have full support in the C and J style and I style. But it's the C and J style. In I style, which is the iOS classic kind of style, every command is a commit. So there's no transaction support where you bundle several commands together like you do in C style or restconf, netconf or something. So in C and J style, you write the number of commands and then you commit. So as an MP, every command is commit. JSON RPC, which is kind of the web UI interface, has full support for candidate manipulation and commit to the candidate. And the same thing with the kind of application programmer API, the management agent API, full support to manipulate the candidate and do confirm commit and so forth. So if you look at it from what does this mean when we put NSO and ConfD together, or a network-wide transaction capable manager, could be some other than NSO, could be another netconf server than ConfD, but let's look at ConfD and NSO here. You see in all these phases, we come in, you do a commit or a netconf edit config to NSO, and NSO will go through kind of the same steps as ConfD does, with the difference of the prepare phase meaning something different with NSO here, that you update CDB and you actually have a NED manager that uses, in this case, the netconf NED to do an edit config to, might be 1, 2, 3, 4, 5 ConfD netconf client server instances that you do a confirmed commit with and go through these phases that we went through before, and there's abort and so forth. So this is what it looks like, and what this means really to NSO here, that there's a candidate and so forth, there's a two-phase commit down here, is that it becomes a lot simpler for NSO to manage such devices or virtual instances or something, because most of the intelligence of the transaction will be handled by the server in that case. If the server is capable of supporting two-phase commit through a candidate and even a three-phase with commit confirmed, that makes it really easy for a manager to manage multiple devices, deploy a service, do a service to device mapping, and then send the configuration to each device, the kind of thing that they need so that this service is implemented. So like we said in the beginning here, there's a lot of things that can go wrong. So, again, the benefit of these very robust transactions is that, well, it becomes much easier for the application, and the application can save a lot of code through it. You can pretend there's no crashes. You can assume that the device will sort out the order of things. When it comes to ConfD, the subscribers would use the priorities the subscriber priorities to sort that out. For example, I want to delete of an interface before someone creates the interfaces or virtual interfaces or something like that. So I know what's going on. All right, so you know that there's no one accessing some overlapping access to the database. You have the isolation guaranteed. So you have, you can lock, for example, the candidate data store with netconf lock or something like that. And you also have the transaction lock that makes sure that when there's a transaction that's committed or that's going to be committed to the running data store, for example, you have a transaction lock on that, and then you have a transaction ID to identify every transaction. And we'll get to why that's important. Yeah, so then you have things are written to disk. So, if you have crashes, race conditions, and so forth, disk failures. So the NSO, netconf, or netconf client, whatever that is, doesn't have to worry about that. So then we said that not every device want to or can implement full transactions with this. Network-wide transactions, which are strict, lockstep order, set the config in the devices. What happens is that if you do that, then if you have one or more very slow devices in your network, and you go through all these steps with committed the candidate, like we've shown on the previous pictures, then you would have to wait for the slowest device that's actually in your network where you're committing this transaction. You go in this lockstep order. You set the candidate, you validate, you go through the prepare and commit phase, and then you come back. What you can do instead with, for example, NSO is to use, you shave off a little bit of this consistency of always having the same configuration or the configuration for the service in all devices at the same time, basically. And you can say, okay, I put this into different queues so that you have a queue for this device over here and then the other device over there, so that they consume these transactions in the pace that they can consume it. So I don't have to wait for them necessarily. And this can be good to then combine with network-wide transactions. Like you have 99 really fast devices or instances, and you have one that's really slow. It's old stuff, but it doesn't really have to receive the configuration at the exact same time. There will be no problem. The network the service that are deployed will work just fine if that comes later. That's fine. It's just some logging service or something like that. And then you place it into commit queue, and you don't really wait for that. You do your network-wide transaction to other devices, and when it's ready to consume this transaction, the device does it, and it becomes consistent with the rest of the service deployment. All right, so there's this good NSO developer days. NSO developer days, if you check that out, sometimes great information about, from a menu perspective to devices. And there's a lot of things that applies to, if you're equipment vendor, there's a lot of stuff that in those NSO developer days that applies to you too, I'm sure. You can find them on YouTube. There's also on the NSO community pages, links to that. All right, so CAP theorem, why do we want to bring that up? Well, it's this combining network-wide transactions with commit queues. Why does it make sense? That's why I want to bring that up. Bring it up here. So this is, CAP theorem was formulated in '98 by Eric Brewer here. He show that, you can't really have consistency, availability, and partition tolerance, which means that there's a distributed system. There's more than one device, then we need partition tolerance. So you can't really combine them and achieve the X here, or the cake that you see in some pictures. So what we do with network-wide transactions is to make sure that we always have consistency, which means that, okay, it's distributed system, so we need partition tolerance. So we try to get as close as possible to also maintain availability, but due to these transaction locks, the device will be unavailable for adding more new configuration in a short period of time. And that short period of time and how short it is depends on much on the application, of course, the size of the configuration that goes down there. And it also depends on other things that we'll get to. So with commit queues, we take away some of this consistency and well, as little as possible, and go to being eventually consistent. It might not matter because this logging service, if it becomes eventually consistent with the rest of the service deployed configuration to various parts of the network, doesn't really matter. So that's what we achieve here. We achieve better availability because we don't have to wait for it. So the lock doesn't have to be as long as it has otherwise. All right, so when there's only one single device to manage, we don't really need partition tolerance. And then we have, consistency and availability. We don't have to do a trade-off really. And I've seen people use commit queues with NSO with one single device, but that's just silly. Don't need to do that. All right, so the common performance opportunities, well, there's a lot of them, but the most common ones, let's bring those up here. As of course, you as a subscriber, if you have an application that's validating, that's subscribing to prepare notifications or commit notifications, if you act as fast as possible as an application here, because the transaction lock is not released until you actually said, okay, I'm done with the transaction. I've read everything that I need to read, so you can write the next transactions in there. The longer time you take there, of course, the longer the transaction will take, and the lock will be set. So the availability is waiting for you when you are an application subscriber here. And the same thing with a data provider external database. That so if you have an external database, same thing there as with a subscriber. The faster you can act on these different steps in the parts of the configuration or Jang models that you want to serve with an external database, the faster, of course, that the transaction lock will be released. Then inside of here, these multiple different stages from NSOs, validation, and read, write, and so forth. When you have your when and must expressions, must statements with the XPath expressions, it's really key to know what you're doing with XPath, and it can be hard to know what one's doing with XPath until one tests. Of course, you have developer logs that show you how much time it took to validate or read and write and so forth. And if you see time going up there, you have the XPath trace log that can turn on in ConfD and also with NSO to see, okay, is there something here that I'm executing a lot? Or is there something where I think ConfD is doing the wrong thing with its very general XPath engine that's there to calculate what you want to do. So there's a lot of things they can do actually wrong with XPath evaluations. For example, you have two big lists and you want to count and make sure that you have unique, that this is something I saw recently, you have unique instances in each in instance of something someone adds to an interface list that actually there's several interface lists, but then you have large lists like that and a routing table, and then you want to count and see that you're unique between these different tables or lists. And it just takes a long time instead of using a simple tailf extension that can help you out there and do it in linear time. You do something that actually is in big O notation than exponential time, or exponential complexity, I should say. So XPath evaluations, just be really careful with those, what you're doing. We have ourselves had to improve our XPath engine because it sometimes did things that were not optimal, and there's still things we're working on. But as an application, it's really important that you also take responsibility there and check it. So that's a common thing. All right, I mentioned commit queues. That's a good thing of dividing your, either do everything with commit queues if you have no consistency worries when it comes to that. You can even take away the atomicity between the different service deployments and the sets of configuration you deploy to devices, and get off the hook completely with consistency. But you can also combine network-wide transactions with commit queues, which is a really good thing there. Of course, doing it as much as possible in batch things when it comes to actually putting stuff to a service in NSO. What takes time is actually creating then the service and mapping it to a device and sending out the device configuration. So the more service configuration you change at once, for example, writing from multiple threads or not setting it just one by one, different parts of the configuration, service configuration one by one, and then map it to one device here, one device there, and then a commit for each. You want to avoid that, so you want to batch things together. This is certainly what here's the most kind of programming tactics, of course, so it's nothing new. Then you have create and the pre-lock create, which is kind of a difficult thing to manage, but you can delay when you create the service in NSO, you can delay the actual transaction lock a little bit, which can be a good thing. So you can write in more data again to the service configuration that is then going to be mapped to all these devices, these 1, 2, 3, 100 devices. So really high level, that's where the performance opportunities usually are when it comes to integration with these things. Other issues are, okay, so if you in a device implement a device, and this is very common, there's many ways of doing this, but you can have uncontrolled out of band changes. What that means is that, okay, I'm over here on this device here. I have these CLI interfaces and so forth, and then I have this manager, which might be NetConf manager and NSO and machine-to-machine communication and so forth. Might be writing a lot of stuff to this device here, but then you have a human coming in and over a CLI interface and at the same, for the same type of configuration that this manager here sees, which is what in these dotted lines here, this manager here does not see the other parts of the configuration. So if you write to that part of the configuration, that means the manager will be out of sync, and then what's even worse is that the service is out of sync, because that can be hard. You might have 100 devices and you want to then reconcile the configuration from some of the devices up to the service. So you're kind of doing the reverse thing here. You're not mapping to the devices, you're mapping from the devices to the service, which can be quite tricky in many instances. So that's good to think about. The kind of second best thing, if you want to avoid out of control band changes, which of course you would do, is to have controlled out of band changes, which means that then you don't touch the parts that are visible to the manager, only the parts that are not visible to the manager. And that's a good thing. Then the manager will not become out of sync. Today, the manager here and so would need to turn off the transaction ID. The transaction ID would be guaranteed that the whole set of configuration has not changed, and it will here in this case. So the transaction ID would change, and then so would think it's out of sync if you use that. So you turn that off. What's coming now, a colleague of mine, John Lindblad, he has a draft, a transaction ID draft in that does something similar to what RESTconf actually does. RESTconf has a transaction ID on each, on different parts of the database and so forth, and the transaction into those, what represents by Yang model, then the kind of schema here. And you can have several transaction IDs. So you can say, okay, this is one transaction ID, this is one, and then you have one here, so that, you know, NSO or some other manager doesn't become out of sync, and can check if they're in sync. It doesn't have to be, that's the most important part, doesn't have to do compare config, which is very time consuming to do. Of course, if you have a large set of config down here, you want to read it up here and compare what you have in the data store over here. That's a rough thing to do. Perfect world would be no out of band changes. You map your service to the data and just, there's no one else managing here. All right, another issue here is, you know, you have hardware and you're changing the setup of hardware, you put in a line card there, take it out. NMDA is the perfect thing here for that. It adds these conceptual or logical data stores, I should say, intended data store and operational state data store, so that you know, when you slide in a new line card, you update the operational data store. There's a notification that goes to the netconf client. The netconf client can then set the intended to whatever it wants this line card to have for a certain type of configuration. But first, reading out the sort of operational data here if it wants to. So that means that there will be no out-of-band changes or spontaneous configuration changes to running data store. It will only be done to the operation data store. And the netconf client can then become aware of that and doesn't have to do a sync from or something to read all the configuration back and then go again sync with the service, which can be hard, as I mentioned. So there's these interfaces example. I won't go through that now, but all right. Performance, then we talked about that. You know, measuring performance, it can be kept very simple, of course. The performance tools that you have in ConfD and NSO is nowadays we added something called the progress trace, and the progress trace will give you all these numbers. When you actually done a commit, you can see all these numbers of how much time certain steps in the process have taken, and you can identify, okay, where is the time taken here if you think that your transaction is going slow. And what's also good is that this progress trace kind of putting timings on each step has also been added to the developer log. So the progress trace now basically adds, what it adds to ConfD is that you can store it, you know, in operational data store, not only to a file, and you can do all sorts of things with the progress trace. But usually where you begin is just check out the developer log and see the time is there. This is done in 7.1, I think. So I want to also highlight that this, for those of you who want to look into NSO, this is great best practice performance and scaling. Just click on this link when you have access to the presentation, or just Google for it and you'll find it. There's a lot of good stuff like this where the timings are explained in what's going on here. For example, with when you do a commit queue, how does what is actually going on there when, and how is the parallelism achieved using commit queues, and what is it that you're taking away here from consistency, and what's your gain time-wise? Where is the gain? All right. Last slide. So there's developer spaces on GitHub where you have, besides examples that come with NSO ConfD, you also have demos. Of course, I want to highlight those as well, besides our community pages, like the developer community for ConfD and NSO, quite active. These demos are good, and we want to expand on that. We have a few useful ones over there on the ConfD side, lots of them with NSO as well. And you know, you can actually add demos or point out problems, or actually correct problems. Just do a pull request, and I'll, or one of my colleagues will accept it if it's for the ConfD demo space. All right, that leaves us 3 minutes for questions, right, Nabil?
Thank you, Connie. So check your Q&A, my Q&A tab, to see if there are questions there. And also, there are a couple of questions here on transactionality. So when you set, not really transactionality, but when you set configuration on a device, right, and the configuration doesn't kick in right away, there is a state, right, that keeps that configuration. I think the system might report different data to the northbound manager. So I guess this question is really after configuration is set in a system and the transaction is valid, committed, everything, it looks good from the manageability perspective from that layer. But then the system still fails later on that configuration. I guess some of the current practices today is that the manager will try to synchronize with that device, right, to get the configuration that the device thinks is the right configuration. So it's really the concept that we're trying to move away from.
Yeah, I mean that's the point of this point of no return here. So when things have been written into the data store here, when you pass the point of no return, that's visible then. So while your application is handling the updates here in the commit phase, that if you read from the northbound interface, you will see that configuration at the same time. Even though the transaction lock is still on, you can still read in all these phases, but here it switches over to the new configuration. That's why it's point of no return. You won't set it back. The only thing that might happen here is that someone reads, and then we have a confirmed commit ongoing, and that confirmed commit is aborted, canceled, or you have a timer that times out. Then you will see that, okay, there was a new transaction and the configuration changed. And while you were reading, not while you were reading, when you're reading, you will read out what's in, for example, the list and so forth. But if you read again, you might see a different configuration. So we are guaranteeing that, okay, you will not get half the list or something like that. That's so all the reads are also handled in read transactions.
Right. Thank you, Connie. So basically, in this, based on this picture we see right here, there are several phases, right? And there is the no point of return part by which we should make sure that our system is not going to fail that configuration, and even if it fails it has to take care of getting back to that configuration state that the user intended. So basically, it's considered intended configuration, right? Correct. And we should strive, the device should strive to reach that state. If there is an error, what are the mitigations to that? So if the system can't do that, right? So what would you say all the mitigations would be in that case, Connie? Keep trying, right? Raise alarms, let the northbound user know that there is a...
Yeah.
Right.
Yeah, so let's go to this confirmed commit picture. Was the best one, I think. Yeah, so US application, you can abort, for example, the validate phase. You say, okay, this doesn't really validate, or the candidate doesn't validate, or the running doesn't validate. Or in the prepare phase, I see that, okay, my system is out of memory, so I have to abort this transaction or something like that. You can do all these things, and you should do as much as you can with the must expressions, patterns, ranges, and then validation points if you need them, so that it can be validated already here. So nothing has been set in other devices or your device. So the best thing is then that you abort it here when for example, NSO says, okay, validate this candidate configuration. Then the second best thing is, of course, that you validate again, sort of when you come down here, or you skip that, you can choose. or in the prepare phase here, you see that, okay, I'm out of memory, I want to abort. Because now nobody has read the configuration. If there are several readers of the configuration at the same time, it's this transaction writing, nobody will have seen this. And the applications that know that, okay, I might set something here, but if something goes wrong, I use ConfD to get the inverse already here of the configuration. So then when I pass the point of no return, I've done all that I can as an application to make sure that, okay, nothing happens after this. But as you mentioned, Nabil, if something happens after here, you typically want to sound the alarm to the netconf client or NSO to say, okay, something went wrong in my device. Then, of course, if it's a confirming commit, you can't do that as an application, but it might happen so that you get as an application, just get an inverse configuration. If another device failed at this stage or this stage over here, now your device went well, but since NSO or the netconf client want to abort this configuration as a last resort, it cancels commit or you get a timeout, then you will get an inverse configuration. But you can see, of course, you can use the ConfD API to check if that's an inverse or not, but it shouldn't matter to your application.
Great. All right, thanks, Connie. I think we don't have any other questions. Thank you, Greg, Wei, Jonas, for helping with the answers. I will make the recording available for everyone later on today. If you have any further questions, you can reach out to me. I'll be able to redirect you to the right resource. Okay, so with that, thank you, everyone, and have a nice day. Take care. Thanks, Con.
Thanks, everyone. Thanks, Nabil. Thanks, everyone.